Okay friends, we will continue with some more examples on Bode plot. Last time we were discussing about the plot for a function of this form 1 by s squared plus 5s plus 100, that is twice zeta omega n s plus omega n squared. For different values of for different values of zeta, you will find this peak value occurs at a shifted point here. That means the peak gradually shifts to the left at a frequency omega d, which is equal to omega n into root over of 1 minus zeta square. Omega d equal to omega n into 1 minus zeta squared. When zeta is small, we can approximate this to omega n. Now we come to a frequency plot, phase plot. Let us once again compute the phase for each of these factors, like say 1 by s plus 10, 1 by s plus 20 and so on. If you have a factor like this, what will be the corresponding phase? If I put s equal to j omega, so omega equal to 1, omega equal to 10, omega equal to say 5 and so on. When it is s plus 10, that means 1 by j omega plus 10. When we take omega equal to 1, how much is this? 1 by 10 plus j. Okay. So, 10 plus j, how much is the angle? Tan inverse 1 by 10. Tan inverse 1 by 10, that is tan inverse of 0.1. Okay. So, that gives me tan inverse of 0.1 with a negative sign. So, that will be minus, how much is it? Tan inverse 0.1 is 0.1, tan theta is equal to theta when theta is small. So, 0.1 radian, approximately 6 degrees. 57 degrees will become 1 radian. So, 0.1 radian means 5.7 degrees, approximately 6 degrees. Okay. If I take 10 times this frequency, that is when omega is 100, then it will be 10 plus 100 j, all right. So, how much is tan inverse 10? Tan inverse 0.1 is 0.6. So, just 1 by 0.1, that means 90 minus 6 degrees will be 84 degrees. Okay. So, we will make a table like this. Omega, if the function is like 1 by s plus some omega c, some critical frequency, then omega, if it is omega c by 10, that is 0.1 times omega c and 10 times omega c, then the corresponding thetas are, this will be minus 6 degrees and this one will be 90 minus 6 degrees. So, minus 84 degrees, it is just complement. Is that all right? If it is similarly, if it is 0.2 omega c, approximately it will be double. This is an approximate calculation. So, similarly at 5.2, so inverse of 0.2, how much is it? 5 times omega c, it will be approximately 78 degrees. Okay. No, omega c at omega equal to omega c, how much is it? Minus 45 degrees. At 2 times omega c, tan inverse 2, 63 degrees. 1 by 2, 90 minus 63 degrees, 27 degrees. This is good enough to make a sketch. Suppose this is 0.1 omega c, this is omega c, this is 10 times omega c. Then for a factor of this kind, it will tend to 0 as omega tends to 0, okay. But we need not go down further. At this point I know it is minus 6 degrees. At this point I know it is tending to minus 84 degrees. Okay. It will asymptotically go up to 90 degree only, 1 by, when s is very very large compared to omega c, it will tend to 1 by j omega, that is minus 90 degree, it cannot go beyond that. So, asymptotically it will be approaching minus 90 degree. Okay. And at omega equal to omega c, it is 45 degrees. Okay. You can take some intermediate values, like at 0.2 it is 27 degrees and so on. So, approximately we can sketch the curve like this. If you take the intermediate values and if the scales are selected properly, then you will be getting a curve like this, okay, for any factor like this. Now, let us see what will be the phase plot for a general function g s, say equal to s into s plus 20 by s plus 10 into s plus 100. For s, it will be giving me plus j omega. So, it will be plus 90 degree, a component like this. All right. Angles are all added, is it not? Theta 1 plus theta 2 minus theta 3 minus theta 4 and so on, that will be the total angle. So, I can, like in the gain plot, if I take log, they become additive. In the phase, you do not have to bother, they will be always additive. So, theta 1 plus theta 2 minus theta 3 minus theta 4, if they are in the denominator, it will be negative. So, this will be theta 1 equal to 90 degree. Theta 2, if I take this one, s plus 20. So, suppose this is 10, this is 100, then somewhere here 20, it will have s plus 20, means this is a critical frequency. So, it will be 45 degree plus 6, 20. So, at 200 it will be 84 degrees and so on, a curve like this. That means, this very curve, if I take the mirror image, this will be reflected here if it is in the numerator, all right. A similar curve will be there in the numerator function. So, this kind of curve will be there. Then 1 by s plus 10, so it will be minus 45 degrees, somewhere here, and again this will be approaching minus 90 like this, and at s equal to 100 there will be again another function like this. One thing is very interesting, if I fix omega c, then I know at 1/10 this frequency it is minus 6 degree, at 10 times this frequency it is minus 84 degrees, and at various other frequencies I know where it will be some 12 degrees, 27 degrees, 63 degrees and so on. So, this curve is fixed, the central point is omega c where the angle is minus 45 degrees. So, I will just take a stencil, I will just cut a piece of paper, say maybe sorry, a cardboard, and then I slide it over this entire scale of frequency, fixing omega c at the requisite point. Do you get my point? So, this omega c in this particular case is fixed here, then it is sliding down this, and that at 100 omega is equal to 100, I again draw this curve, the same curve, all right, and then I take its mirror image, just invert this and then take the curve at omega c is equal to 20, all right. So, I can prepare one slide, I can prepare one stencil, just take a cardboard and then cut it along this, all right, prepare, say take from the market any similar graph sheet, so that these decades are already fixed, it can be matched with any graph sheet, okay, and then you make a profile like this and then use it. The same stencil can be used for drawing all the phase components and then add them together. Okay. So, here it will be plus 90, then it is gradually falling because S10 comes earlier. So, it will be falling like this plus minus so much. So, it will be slightly less. So, it will be falling like this, and then gradually this will start coming. So, the rate of fall and rate of increase they may be more or less same. So, it may remain horizontal, and then again a fall starts at around this point. It is falling, mind you, very slowly, because here this is increasing, here it is, this is decreasing here and this is increasing, but they are not at the same rate. Somewhere here again additional term comes. So, fall will be much faster. At the end this is minus 90, minus 90, minus 180, this is plus 90, plus 90, 180. So, finally, it will come down to 0. Okay. And so on. So, phase plot is much simpler. What you have to draw is first around omega c, draw this curve for one single phase, one factor, and then keep on repeating that, all right, like this, and then add them together. The network functions, sometimes we are interested in knowing, say, what will be, say, y or z parameters for a general network, 1 1 dashed, 2 2 dashed, and what will be its variation with respect to frequency. So, you may be given maybe something like a transmission line. Say. What will be V2s by V1s? I excite it by variable frequency source, then R1, L1, R2, L2, C. What will be V2 by V1 in the Laplace domain? If I keep it open, how much is V2 by V1? So, it will be 1 by Cs divided by R1 plus L1s plus 1 by Cs. This will give rise to a quadratic. See, if I multiply throughout by Cs, it will be L1 C s squared plus R1 C s plus 1. So, this is a quadratic, depending on the value of R1, L1 and C, you will have different values of zeta, roots may be complex, all right, or real, and you will get V2 by V1 for different values of omega, something like this, is it not, 40 dB per decade. So, for any frequency you can know what will be the gain, all right, for any frequency you will be knowing the gain. So, if I give an input voltage, you can calculate output voltage immediately once you know this function. We may be interested in Y or Z parameters, that is short circuit or open circuit parameters, ABCD parameters and so on. So, all these can be computed in terms of S, we will get a function like this, and then from the Bode plot you can get the response at different frequencies. So, let us work out one or two problems. Now, before we go to numerical problems, let us discuss about the inverse problem, that is an identification problem. Given an experimental data, can you estimate the transfer function? Quite often we do experiments on a network system which is maybe in the given which may be given in the form of a black box, all right. I may be interested in the transfer function V2 by V1. So, we apply a voltage of frequency varying from say 1 hertz to 10 kilohertz, all right. You measure the ratio of the voltage V2 by V1 at every frequency. Suppose the experimental points V2 by V1 will give you gain, V2 by V1 will be giving you gain against frequency. For different frequencies you measure the ratio and then take 20 log of that ratio V2 by V1. You may be getting some experimental points like this. They will be scattered around some approximate straight lines. You are approximating them, mind you, by the best fit. Suppose we get some lines like this. You should attempt to fit these points along either a horizontal line or a 20 dB per decade slope or a 40 dB per decade slope as far as possible, because you cannot have a system function. Why 20 dB per decade slope? Can I have 30 dB per decade slope? Can I have 30 dB per decade slope? Can you have a function s to the power 3 by 2 plus 10? No, you can have 1 by s plus 10, 1 by s plus 10 whole square or a quadratic, but power of s cannot be a fraction. And from all these we know the asymptotes will have to be either 20 dB per decade or 40 dB per decade or a horizontal line. It cannot be anything other than that. So, you have to match these points as far as possible. They are all experimental points, so there can be errors always. Best possible fits with these lines. Once you have identified this, you know these frequencies omega 1, omega 2, omega 3 and so on, you can write the transfer function. Once you have written the transfer function, you can also obtain the phase, all right. From the transfer function you can draw the phase, and while doing the experiment you also put a phase meter, measure the phase, see whether the experimental phase values and the estimated phase curve they match closely or not. If they do not, then you again try to fit in another set of 20 dB per decade and horizontal lines, so as to get the best possible combination. That means, 2 experimental data set will be given to you, you have to make best possible match for the transfer function, all right. This is an identification problem. So, let us identify 1 or 2 functions. Okay. I have got 50 dB, this is 20 log of g, this is 40 dB, this is 20 dB per decade, 40 dB per decade, this is omega 1 10 radians per second, this is omega 2 that is 20, and this one is omega 3. Omega 3. That is 100. Okay. What will be the transfer function? Can you suggest what will be the function like? Yes. Can I write s plus 10? Okay, s plus 10, that will be, this curve is falling at 20 dB per decade. So, s plus 10, then at 20 numerator s plus 20, fine, then s plus 100, very good. S plus 100 is what? Squared. Yes, s plus 100 from this point onward it is 40 dB per decade. So, squared, that is all. There is a gain. Is that so? No. K into 20, s plus 20 can be written as 20 into 1 plus s by 20. It is 1 plus s by 20 which gives me 0 dB line and this, okay, divided by 10 into 1 plus s by 10 multiplied by 100 squared into 1 plus s by 100 squared. Okay. So, that is equal to k by 20, so 2 by 100 squared into these functions. So, it is 20 log of this which is equal to 50. So, find out k and you can substitute that value of k here. Is that all right? So, 20 log of this quantity, how much is it? K by 50,000, 5,000 is equal to 50, whatever that may mean. So, that will be giving me the value of k. Is that all right? There is a problem. $20 dB per decade, slope is there, this is omega 2, this is 10,000. this is 2, this is 40 dB per decade. Okay. And this is 12, this is 20 log of g. Can you estimate the function? Can you estimate this function? No, this is 10,000, this is 20 dB per decade slope, this is 12 dB. How much is omega 2? Question is, what is the value of omega 2, omega 1 and then Gs? Is that all right? Now, this is 20 dB per decade. I can conceive this as 6 dB per octave. So, this is 12 dB. So, when is it rising by 12 dB? That means it has fallen from here to this point 0 at a rate of 6 dB per octave, and this fall is 12 dB. So, how many octaves are there? 2. That means, what is this frequency omega 2? 10,000 divided by 2 and 2 per octave. There are 2 octaves. Had it been divided by 2, that means this rise would have been only 6 dB. So, 6 plus 6, 12 dB. So, 12 dB fall or rise, if you take it from the reverse side, will be at 10,000 divided by 4. Is that all right? So, omega 2 is 10,000 divided by 4, 2500 radians per second. What about omega 1? What about omega 1? This is 12 dB this is 12 dB fall, and 40 dB per decade means 12 dB per octave. So, this is, if this is 2, how much is omega 1? Just next, twice this frequency. This slope is double that 20 dB per decade. 40 dB per decade means something like s squared. Okay. So, 40 dB per decade rise is as good as 12 dB per octave. So, it has gone up by 12 dB, then this is 1 octave, that means 2 multiplied by 2, 4, omega 1 is 4. Is that all right? So, how much will be Gs? Therefore, some k into, what should I write? K into S plus 4, S plus 4, S plus 4 whole square. Where is 4 coming? S square in the numerator or the denominator? S squared denominator. S square in the denominator means it will be falling. S squared in the numerator, and then in the denominator S plus 4 whole squared, because 40 dB per decade will have to be counted. So, it also has to be whole squared, and then S plus omega 2 2500 what? Only S plus 2500? Yes, it is 20 dB per decade. And then how do you evaluate K?
That gain taking outside and that 4 and 25 and 20 log of all this.
So, you can evaluate at any point here. Okay. Any other method?
That 4 and 25 will take common. That 4 and 25 will take common and
This will be an see, mind you, these are all asymptotes. So, for evaluating that, you may get 2-3 different values if you evaluate at 2-3 different points, all right, because there is an approximation. So, you have to take the values which are to be neglected, you have to take that into account. So, whenever you are taking a point, say somewhere here at omega equal to 1, at omega equal to 1, how much is this? At omega equal to 4, how much is this? 12. At omega equal to 2, 0. Then half of that frequency, at half the frequency it will be minus 12. This is plus 12, this has to be minus 12. They are of equal length so far as the logarithmic scale is concerned. This is 2 times, this is also 2 times. Is that all right? So, this is minus 12 at omega equal to 1, and that time this is neglected, this is neglected, you are considering only asymptotes. So, at omega equal to 1, it will be 20 log of k and this will be 0. So, 20 log of k is minus 12, calculate k. Is that all right? So, 20 log of k is minus 12. So, log of k is minus 12 by 20, that is 0.6. So, k is how much? 0.6 minus 0.6. Four or 1 by 4. Log of 4 is 0.6. So, log of anti-log of minus 0.6 will be 1 by 4, that is 0.25. Is that all right? What will be the plot for s square plus s plus 4 whole squared? You have got some problems, okay, or s squared plus 9 divided by s plus 4 into s plus 20. Let us take up these two problems. 1 by s squared plus s plus 4 whole squared. What will be the sketch like? 20 log of g. So, the first one we will plot here. 1 by s squared, what will be the plot like? Suppose this is 1, this is 10 and so on. At 1, s square, 1 by s squared etcetera will be passing through 1, and at what slope? 40 dB per decade, it is s squared, 40 dB per decade will be the slope here. All right, let me draw it clearly. And then at omega equal to 4, how much is it? Again another 40 dB. So, it will be 80 dB per decade. This will be the slope. This is 40 dB per decade and 80 dB per decade. It is all right if it is written as 1 by s squared into 4 squared taken outside 1 plus s by 4 whole squared into 1 by 16. Okay. So, log of 1 by 16 will have to be added with this. So, it will go down further. A similar curve, log of 1 by 16 will be negative minus log of 16. How much is log of 16? To the power 4. So, 4 into 0.3, 1.2. into 20 minus 24 dB. So, the whole thing has to be brought down by minus 24 dB. Is that all right? It will be somewhat like this. So, at this point it is minus 24 dB. This is minus 24. Let us see this function s squared plus 9 by s plus 4 into s plus 20. How does it look like? S squared plus 9 by s plus 4 into s plus 20. So, s plus 4, so if I take 4 here, this will be one component, these are the asymptotes. S plus 20, if I take 20 here, again this will be another component, both with slopes 20 dB per decade, 20 dB per decade, and s squared plus 9, s squared plus 9 will be at 9 or at 3, square root of 9 is 3. So, before this what will be like? Some constant, it will be shooting up to infinity, and then from there it will be falling at 40 dB per decade, it will be falling much faster. So, it will be, will it be this way? Will it be this way? Last time when we studied, it was 1 by s square plus twice zeta omega n s plus omega n square. Now, it is in the numerator. So, it will be the other way, and then 40 dB per decade. Okay. So, if you are having a numerator function, then the peak will go down and then go up. If it is in the denominator, then it will go up first and then it will go down by 40 dB per decade. Is that all right? So, now it will be sum total of these 3 components. This peak occurs at omega equal to 3, then this one at omega equal to 4, 20 dB per decade, and omega equal to 20, 40 dB per 20 dB per decade. So, 20 plus 20, 40 dB fall, and this is 40 dB rise. So, at the end the resultant, if I can sketch the resultant, it will look like this. It will be a function which will be going like this, and then 20 dB fall and 40 dB increase. So, from 4 onward it will be 20 dB per decade net result, all right. And then from 20 omega to 20 onward it will become horizontal. So, the net result will be somewhat like this. 3 and 4 are very close. So, you will not be able to see 40 dB slope anywhere, it will be gradually going up to 20 dB per decade slope, and then finally catching up with the horizontal line. Another interesting function, suppose you have s squared plus twice zeta 1 omega n 1 plus omega n 1 squared divided by s squared plus twice zeta 2 omega n 2 plus omega n 2 squared. That means, you are having 2 such quadratics with complex roots. Suppose omega n is greater than, much greater than omega n 2, omega n 1 is much greater than omega n 2. So, the numerator starts appearing first, is it not? So, that will give me a function like this. Depending on the value of zeta, this will be very peaky or maybe flat, all right. We are not interested in actual value of zeta at this moment. Similarly, the other one, it will have, this is somewhere close to omega n 1, say approximately omega n 1, and somewhere here omega n 2, omega n 2 is far off. It will be falling like this. So, I am just putting two different dotted lines. So, what will be the resultant like? It will be this one going up like this, and then if I add up these two, it will be going up and then gradually this is 40 dB per decade and this is 40 dB per decade. So, they will be cancelling. Okay. If they are reasonably separated, then the resultant will look like this. Okay. Now, tell me, if I have S plus, sorry, S minus 10 by S plus 10, what will be the gain plot? What will be the gain plot for this? S plus 10 by S minus 10. So, let us compute G magnitude. G magnitude is 10 plus, how much is it? 10 squared plus omega squared under root for the numerator divided by 10 squared plus omega square under root, that is always equal to 1. What is it? All the time gain is 1. What is this called? What is this called? Non-minimum phase. It is an all pass filter. All the frequencies are allowed with the same gain. All right. So, for an all pass filter, what is the Bode plot? Zero. That means, if I draw a horizontal line, it can be S minus 10 by S plus 10, it can be S plus 12 by S minus 12 by S plus 12, anything. Can you identify? Where can I identify that this function is phase? So, what will be the phase plot like? So, 20 log of G and omega, it will be 0 dB all the time, and for phase, yes, S minus 10, what is the angle? Let us see what will be the angle. It is minus 10 plus j omega. Minus 10 plus j omega is what? What would be the value? Which quadrant is it? If you take your calculator, if you take the tan inverse b by a, you will be always getting the prime value as, say, omega equal to 10 minus 45 degrees, but actual value is minus 135 degrees, because it is minus 10 plus j 10, say. So, it will be this angle, but if you take plane ratio, you will be misled, you will be taking this angle, is it not? Tan inverse of minus 1 is minus 45 degrees, but it is also 135 degrees. So, it is this 135 degrees that has to be taken, because it is minus 10 plus j omega. and 10 plus j 10, that is 45 degrees. So, 45 degrees in the denominator and numerator minus 135 degrees will give me minus 180. So, at omega equal to 10 it will be minus 180. So, like that you can make a plot. Okay. So, if you take omega equal to 10, say, it will be minus 180. Omega tending to 0, say omega equal to 1. So, it will be 1 minus 10 plus j 1. How much is it? Minus 10 plus j 1, almost minus 180, minus 6 degrees, 174 degrees. So, that will be minus 174 degrees, and this one will be plus 6, 10 plus j 1, that will be plus 6 degrees. So, that will become minus 180 degree. So, it will be always minus 180, always minus 180. I will request all of you to think over it, and we will have a discussion on this phase plot. Okay. And also, what will be the nature of variation of the phase for a quadratic like this? How will the phase change? So, many such examples can be taken. S squared plus 6s plus 9 divided by s plus 9 into s plus 50. What will be the Bode plot for this? What will be the gain plot like? Numerator is, I can see b square is equal to 4ac. So, it is s plus 3 whole squared divided by s plus 9 into s plus 50. So, what will be the gain plot like? I can always take the constants out. So, 9 by 9 and 1 by 50. So, it will be 1 by 50 into 1 plus s by 3 whole squared divided by 1 plus s by 9 into 1 plus s by 50. Okay. So, 20 log of 1 by 50 can be taken separately, and let us make sketches for these 3 components. So, 1 by 1 plus s by 3 whole squared. So, let us take this as 3, this as 9, this as 50. Okay. So, 1 plus s by 3 whole squared will be 40 dB per decade. Very good, this slope, and at 9 it will be 20 dB per decade, minus 20 dB per decade, and then again at 50 minus 20 dB per decade. All right. So, what is the resultant of these 3? Resultant will be, if I am permitted to draw by a dotted line like this, it will be actually this line, and then at 9, okay, at 9 this will be minus 20. So, it will be plus 20 dB per decade, it will go on like this, and at 50 it will become horizontal. So, the net function will look like 40 dB, 20 dB and then horizontal one, and then depending on the constant 20 log of 1 by 50, it will be shifted up or down depending on its magnitude. Here it is 1 by 50, so it will be negative. So, it will be brought down by this factor 20 log of 50. Is that all right? So, we will stop here for today. We will take some examples in the next class. Thank you very much. Okay, good morning friends. We will be continuing our discussions on Bode plot. Before we start, I would like to just bring to your notice some small slip that I had made yesterday. I was mentioning about two frequencies, omega n1 and omega n2. If you remember, somebody pointed out later on. What is that? Anyway, it was like this. Omega n1, there was a frequency omega n2. So, what I meant was omega n1 is less than omega n2, and it was in the numerator s squared plus twice zeta 1 omega n1 s plus omega n1 squared divided by s squared plus twice zeta 2 omega n2 s plus omega n2 squared. So, the curve was somewhat like this. Okay. This was omega n2, this was omega n1. Okay. In the phase plot, this was 20 log of g. In the phase plot, we discussed for a function like 1 by s plus omega c, approximately 1/10 of omega c, approximately 1/10 of omega c, the angle was about 6 degrees, minus 6 degrees, and at 10 times this it is 84 degrees. All right. So, it is close to 0 degree and this is close to 90 degrees. So, almost in 2 decades you are having a fall of 90 degrees approximately. So, if one draws a line 45 degrees per decade, in many books they write 45 degrees per decade straight line, and this will be slightly over this and slightly below this. Okay. It is 1 decade around omega c. Okay. So, this is again another approximate sketch in the phase GS. What are the frequencies? There will be some gain k. There is a line that is starting with a slope of 40 dB per decade. So, what will be the nature of the function? Will it be k by s or ks or k by s squared, as you said, k by s squared, k s squared, it is going up. So, k s squared, thank you very much, and then it was going up like this and then it takes a bend at 2, s equal to j 2, then 1 plus s by 2 whole squared. There was a rise of 40 dB per decade and you are bringing it to 0, that means it will be whole squared, is it not? Then 1 plus s by 3, here you are having a further fall of 20 dB per decade. Then anything else? Nothing else, it continues. Okay. Then how do you identify k? So, you have to identify this height. How do you do that? Actually, there are two informations which are redundant. I could have asked for this frequency, I could have asked for this frequency, or I could have asked for this frequency. The question that was given actually given one excess information, the same information. So, you can calculate either from this side or from this side. No, there is no pole. I am taking any value of s. S I am varying along this imaginary axis. All right. Then what does it show me? If I vary s along this, what does it show? Now, for that matter, anywhere if I take, what will be this vector like? This is s. So, minus z plus this unknown vector x, minus z 1 plus unknown vector x is equal to s. So, how much is the unknown vector? S plus z 1. All right. So, if I take any s, it need not be on this line, any s, then a distance, this vector connecting minus z 1 and this will give me s plus z 1 vector. All right. Similarly, for a pole P 1, if I draw this, what will be this representing? This P 1 is basically minus P 1, is it not? Suppose it is at minus P 1, P 1 is a complex quantity, all right, then it will be representing s plus P 1 vector. If s plus P 1 is a factor, then s equal to minus P 1 is the root, all right. So, if this is minus 3 plus 4j, then the factor corresponding to this vector will be giving me s plus 3 minus 4j. If minus 3 plus 4j is this point, then this vector is s plus 3 minus 4j. Okay. Similarly, for this one and so on. Okay. So, in the next class we shall discuss about how to compute these a, b, c, these constants with the help of these phasors or these vectors. Okay. So, we know the location of poles and zeros from the factors, and then we will find out how to compute these residues geometrically. Okay. Thank you very much.